So let's continue on with groundwater and look at more detail at aquatards and aquifers. Recall that an aquitard is an impermeable rock layer such as shale that hinders or prevents water movement, whereas an aquifer is a highly permeable rock or sediment such as sandstone, porous limestone, within the zone of saturation. Now, aquifers can be either unconfined and not bounded by aquatards, or confined where they're bounded above and below by aquatards. So in this figure shown on the top, the upper aquifer, the one near the surface, is an unconfined aquifer. Notice that there's an aquitard below, but there's no aquitard above. And as a result, the unconfined aquifer is defined by the water table and the zone of saturation versus unsaturation. And also the overall groundwater flow is from areas of recharge to areas of discharge, such as nearby rivers and streams. We looked at this in more detail last time. On the other hand, the confined aquifer that occurs below is bounded both above and below by aquitards, and therefore it's constrained and is not defined by a water table or things of that type, nature. Now, a hydrostatic pressure is defined as the weight that an overlying column of water would exert at a particular depth. And water within a confined aquifer, as such, is often under hydrostatic pressure. And hydrostatic pressure creates what's known as a pressure surface, as, for example, in our municipal water system, where there's a water tank in which water is pumped into the tank so that it's partly filled, and the height of the water within the water tank defines what's known as the pressure surface. Now, the pressure surface is simply the level to which water will rise. And as a result, it's the pressure surface that allows our water to flow under pressure when we open the faucet within our homes. In other words, if permitted, the water within each one of these homes will rise up to the level of the pressure surface directly above it if allowed to. Okay. And that's why, for example, if we lose electricity because of a hurricane, we also do not have water pressure. This is because the water tanks are not filled since the pumps are not working. Now, within an artesian system, an artesian system occurs where groundwater under pressure rises above the level of the aquifer. And in order to have an artesian system, two conditions are necessary. One, the aquifer is inclined with one end receiving water, in other words, the recharge area. And what's more, the aquifer also has to be confined with aquitards both above and below. And in this figure shown above, both of these conditions are met. In this case, the aquifer is a sandstone layer that's recharged over in the area towards the left. And once the aquifer moves further at greater depths, notice that it's bounded above and below by aquitards. And as such, that aquifer is trapped or kind of sandwiched between those two aquitards and can only flow further towards greater depths. Now, the actual pressure surface is defined within the recharge area to the left, where it corresponds with the water table. In other words, the boundary between the unsaturated and saturated zone. And from there, we can extend that pressure surface towards the right, as shown in that hypothetical plane in that upper diagram. Now, in artesian wells, water rises on its own without pumping. And there are two types of artesian wells. One type is non-flowing, and this occurs when the pressure surface is below ground and the water does not reach the surface. For example, in this upper figure, notice that, again, when we look in more detail at the recharge area of the aquifer in the previous diagram, notice that the pressure surface corresponds to the height of the water table within the recharge zone. And nearby, just to the right, we have a well that penetrates into that aquifer. However, notice that the water within that well only rises to the pressure surface and does not actually reach the surface of the ground, because the pressure surface here occurs below the land surface. And so that upper diagram is an example of a non-flowing artesian well. On the other hand, within the lower diagram, we see that the pressure surface occurs above the ground, and this in turn creates a flowing artesian well where the water rises all the way to the surface without pumping. So the point is that whether or not it's a flowing or non-flowing artesian well depends on whether the pressure surface occurs below or above the ground surface. Yeah.
What determines the pressure surface?
We saw in the pressure surface, in this case, within the recharge area, the pressure surface corresponds to the water table. And we can project, in that previous diagram, we can then project that pressure surface over towards the right, and that's shown as this hypothetical plane. In the next two slides, we've only looked at well number 1 and well number 2 in more detail. And those are the wells that are shown in this slide. Does that make sense? Okay. It's analogous to the level of the water within that tank in the previous couple of slides back. Okay. Here's another example of a confined aquifer. This occurs just to line of profile we see in that cross section. Begins at the base of the Black Hills in South Dakota and extends eastward across the Missouri River. We can see in the cross section the location of the Missouri River halfway across. But here, the recharge area in this case occurs at the foothills of the Black Hills to the west. And the aquifers include the Newcastle sandstone. There are two different levels of the Newcastle sandstone, which in turn is bounded by aquicludes, which include the Cretaceous shale layer near the surface, as well as the Skull Creek shale and the Madison confining layer that occurs below. Now from there, the groundwater flows eastward into the Dakota sandstone, and from there, wells that penetrate the Dakota sandstone towards the east will then end up flowing water without pumping all the way to the surface. And as a result, this is the area of the flowing artesian wells in this area. Again, the pressure surface is defined to the west at the base of the Black Hills by the height of the water table within the area of recharge. And here's a couple of examples of flowing artesian wells. You see these things around Austin. If you ever drive around Austin, you'll come across these. They look like fountains, but basically these are artesian wells where the groundwater is coming from the hills just to the west. And the figure to the right is really flowing, but I wouldn't bother to drink that stuff because it's probably rich in hydrocarbons. Anyway. Now we can get changes in the water table with time. In regions where the withdrawal of water exceeds the recharge, the water table will gradually drop, and if the water table is allowed to drop significantly, eventually land subsidence will result. In other words, the land surface will start to sink, as we very well know in the Houston area. This map, for example, shows the net result of land surface subsidence that has occurred in and around Houston between 1906 and 1978 as a result of the lowering of the water table. Now what happens is that groundwater withdrawal in the Houston-Galveston area in the early to mid part of the 20th century caused large reduction in artesian pressure and subsequent irreversible compaction of the underlying clays. The result of the compaction is that ground subsidence in excess of 9 feet have occurred in some areas of Harris County. The areas of greatest subsidence occurred in these areas that have the darkest colors. In those places, land subsidence was exceeded about 9 feet over the course of the early to mid 20th century. Now, groundwater withdrawal has stabilized since then because of the increasing reliance on surface water, particularly from reservoirs behind dams like Lake Livingston and so on. But a good example of the consequence of subsidence is the Brownwood subdivision in Baytown, Texas, which eventually had to be abandoned because of the extensive flooding that occurred in this area, mainly as a result of ground subsidence. One of the better known aquifers is the High Plains Aquifer, located in a region of modest amounts of precipitation but high evaporation rates, where little rainwater is available to recharge the aquifer. And we can see that the High Plains Aquifer extends from West Texas up through western Oklahoma, western Kansas, and on into Nebraska and South Dakota. Now, within the High Plains Aquifer, about 170,000 wells irrigate in excess of 65,000 square kilometers of land. And as a result of this intense irrigation, groundwater was significantly depleted in many areas. For example, 62% of the total decline occurred just in West Texas. If you look at the color coding in the map towards the right, the greatest areas of greatest water level change are indicated by the reds and the oranges, where the water level within the aquifer has dropped in excess of 100 feet in many areas of particularly West Texas, western Oklahoma, and parts of southwestern Kansas. So this is a serious concern, because once that aquifer becomes too depleted, crops can no longer be irrigated using this source of water. Another example is the San Joaquin Valley of California, where irrigation began in the late 1800s, and land subsidence occurred since about the mid-1920s, And since then, water levels has dropped by as much as 120 meters or 400 feet by the early 1970s. And the resulting ground subsidence exceeded 8.5 meters or 29 feet in some areas. This is dramatically shown in this photograph to the right. Notice the level of the land before heavy groundwater pumping began, and the present level of the land after 52 years of heavy pumping. This corresponds to substances of land subsidence in excess of 29 feet. Of course, that guy standing there wasn't there the entire time, but anyway. Now, subsidence eventually stopped when imports of surface water increased and the overall withdrawal rates decreased within this particular region. Actually, this guy standing in this photograph, he was 12 years old when land subsidence began, and he pretty much stood at the same spot. And today, when that photograph was taken 52 years later, he obviously aged quite a bit, but you don't think that's funny? Oh, gosh, tough audience. Now, there are ways of recharging groundwater. For example, groundwater can be artificially recharged by, for example, channeling runoff in urban areas into basins, and at that point allowing the water to simply seep down and recharge the underlying aquifer. We can also spread biodegradable liquid waste over the land surface, and as water percolates down to the water table, the underlying sediments will filter out the contaminants. Withdrawn water can also be pumped back into the ground using what's known as injection wells, things of that nature.
So, wouldn't the relatively rapid changing the topography regions have man-made infrastructure, roads, pipes?
Are you talking about land subsidence?
Yes.
Oh yeah, land subsidence can do a tremendous amount of damage to homes, roads. As a matter of fact, a lot of our broken roads, particularly when you get deep sinks, those could be either faults or land subsidence. But you saw that photograph of the Brownwood subdivision. As the land sinks, the area becomes prone to more and more flooding till eventually it just has to be abandoned. But yes, land subsidence is a serious problem in our area in particular. It also damages pipes. When underground pipes break, for example, that can be in part due to land subsidence too. Oh, yeah, it just, if you recall several years back when we had that intense drought and pipes were breaking all over the city, that's because the clays were so dry and became so compacted that the underground plumbing system and drainage system became under stress so much that pipes were just breaking everywhere for the most part. Streets were buckling, and that's all because of the compaction of the drying clay that occurred below the surface. Pardon? No, it's land subsidence is primarily due to either groundwater withdrawal or faults, active faults. Now, what happens with subsidence is that the water table drops, the shales in particular dry, and when shales dry, they compact and decrease in volume. And this causes the surface to sink, and that's mainly what's happening here. Here's an example of a recharge basin. Notice that rainwater collects and flows into the recharge basin by a series of pipes, and at that point is then allowed to infiltrate through the underlying unsaturated zone, and in this way recharge the underlying groundwater system. Groundwater can be contaminated by such things as drainage from septic tanks, broken sewers and barnyards, agricultural poisons like fertilizers, pesticides, highway salts, buried hazardous wastes, and along coastal areas, invading seawater can also be a significant problem. Now, one common source of contamination is sewage. In cases of extremely permeable aquifers, for example, coarse gravel with large openings, groundwater may travel long distances without being cleaned and filtered. On the other hand, sewage can be purified when passing through a few dozen meters of an aquifer composed of sand or permeable sandstone. Here, for an example, is an aquifer composed of a cavernous limestone. And this is an extremely permeable aquifer, which is not effective at cleaning groundwater. Here, towards the right, for example, we see a leaky septic tank and contaminated groundwater flowing towards the left, where we have a well, in turn delivering contaminated water. Notice the time it takes for the water to flow from the septic tank to the well. It's just a matter of days or weeks because of the very cavernous nature of this bedrock. On the other hand, here's a situation of clay-bearing sandstone capable of filtering and cleaning the contaminated groundwater, such as the well number 2 is delivering clean water. Notice again also that the movement of groundwater is very, very slow from the contaminated septic tank to well number 2, taking months to even years to travel over that distance. So there's plenty of time for the contaminants to be removed, particularly with if the sandstone contains a certain amount of clays, because those of us who've ever owned cats and have litter boxes, we know that clays can remove odors and other contaminants. They're very effective with it. Okay. Now here's an example of heavy pumping by an irrigation well, which reverses the groundwater movement, leading to contamination of a nearby small well. In the upper block diagram, figure A, we start out with a shallow well that's pumping clean water, and that's because the leaky septic tank although it's contaminating the groundwater flow is away from the well, and so it does not affect the well in this particular situation. But notice that later on a heavy pumped well is sunk and starts to heavily pump the water for irrigation. That pumping is so heavy that it literally reverses the groundwater movement, so that now that small well is contaminated by sewage bacteria. Yeah, the moral of the story is be careful when you heavily pump that you're not affecting nearby wells. And altering, and make sure that the heavily pumped well is not actually reversing the groundwater flow. Coastal areas can have a problem with saltwater contamination. Notice in the upper block diagram, figure A, we have fresh water overlaying salty groundwater. And the reason is because fresh water tends to be less dense than salt water. And just like in the case of oil and vinegar, or oil and water, you get this separation. And as long as that pumping well remains bottom out in the fresh groundwater, it'll deliver clean water. But that pumped well can eventually pump to the point that it draws in the underlying salt groundwater, in which case the well is contaminated. Now, groundwater can also do a significant amount of geologic work, particularly if the groundwater is mildly acidic. Carbonic acid forms, for example, when rainwater dissolves carbon dioxide from the atmosphere, and also when the rainwater hits the ground and infiltrates through the underlying soil, it can also become acidic from the decaying plants and other organic material. The acidic water will then percolate through the soil and bedrock down to the underlying groundwater system. We all know that acidic water dissolves limestone, and so too acidic groundwater can slowly dissolve limestone bedrock, and over long periods of time eventually create what's called karst topography. Now, karst topography results when slightly acidic groundwater dissolves mainly limestone bedrock, and karst topography can include such features as caves, sinkholes, karst towers, and even underground streams. Let's start out, for an example, in the early stage where groundwater percolates through limestone bedrock along mainly joints and bedding planes. And notice at this point the water table sits quite high to the point that it intersects this stream shown in that block diagram. Now at this stage, the groundwater, if it's acidic, will slowly begin to dissolve the limestone bedrock. As dissolution progresses, sinkholes will begin to grow, and sinkhole and surface streams can even be funneled below the ground. And caves, in turn, are forming just below the water table. The reason for sinkholes is that as caves form below the subsurface, eventually the caves will become large enough that the overlying bedrock can no longer be supported and therefore collapses, forming a depression on the surface. Now, as time passes, caverns will collapse, sinkholes will coalesce to form larger flat floor depressions. And if the water table then drops and the shallower caves enter or are brought up into the zone of aeration above the water table, this is the stage where the cave features like stalagmites or stalagmitites will then start to form within the cavern. Now here's some examples of karst topography. The photograph on the right is an aerial view of lakes, basically sinkholes that have been filled with water. And obviously people are going to have trouble getting to work in this particular situation. Sinkholes occur quite a bit in Florida and also in parts of Kentucky because the bedrock is mainly limestone. What happens in the case of Florida sinkholes is, again, the limestone bedrock. The underlying caves are forming below the surface, and eventually the caves become large enough that the overlying rock is no longer supported and therefore simply collapses to form a sinkhole. Now, several years ago, if you recall, in Dayzetta, Texas, a sinkhole formed and gradually grew larger and larger over a period of days to weeks. Our area is not underlain by limestone. What happened in this case was that a nearby company was injecting wastewater into underground salt dome and was injecting wastewater at a greater rate than was permitted As a result, the underlying salt slowly dissolved away to the point that the sinkhole formed on the surface. Karst towers are the long-term effect of dissolution of limestone. For example, this photograph from southeast China. Most caverns are created, yeah.
How does the groundwater contamination cause the sinkholes?
Now, most caverns are created by acidic groundwater dissolving soluble rock, and dissolution occurs at or just below the water table within the zone of saturation. However, after the water table drops, caves are no longer flooded, but instead open to the air. And at that stage, dripstone, basically freshwater limestone called travertine, can then form spelenethems within the open caves, within the overall zone of aeration or zone of unsaturation above the water table. And here we see that dissolution of limestone that takes place within the zone of saturation, and that's the time that the caves actually open up, open up and form. However, once the water table drops and the caves are exposed above the water table, that's the stage when the dripstones, the spelenethems, will then form within the open caverns. What happens is when the cave is exposed to air, we can continue to have water dripping from the cave ceiling to form what are called soda straws. And as the dripping ceiling, over time, as the water drips from the cave ceiling, it'll also crystallize a little bit of calcium carbonate, calcite, if the water is saturated with calcium bicarbonate. And over time, these soda straws will grow and extend downward from the cave ceiling. And over many, many thousands to millions of years, we end up with these spectacular cave deposits to the right within limestone caverns, simply resulting from the inorganic precipitation of calcium carbonate. And as a result, we end up with these dripstone features, collectively referred to as spelenethems, which include stalactites that are those icicle-like features hanging from the ceiling. Stalagmites extend upward from the floor of the cavern, and cave columns in turn form when the stalactites and the stalagmites meet. Now, water in hot springs are at least 6 to 9 degrees warmer than the mean annual temperature of a particular locality. Now, some groundwater circulates to great depths and is heated by the crust's increasing geothermal gradient, oftentimes guided by deep faults. But water in most hot springs tends to be heated from cooling igneous rock. Here, for an example, Mammoth Hot Springs in Yellowstone Park is heated by an underground magma chamber. Geysers, on the other hand, are intermittent hot springs that occur when groundwater fills extensive underground chambers within hot igneous rock. And from there, the groundwater is heated, expands, and changes to steam, afterwards violently erupting on the surface as these impressive geyser eruptions like Old Faithful. Stages in an eruption of a geyser. This, for example, applies to Old Faithful in Yellowstone National Park, where that's underlain by warm ash and lava flows. And notice there's a network of caverns that are filled with groundwater. Groundwater near the bottom, it then becomes heated to near boiling. And from there, the water higher in the system is also heated, expands, and starts to flow out the top as outflow. This in turn, the outflow in the top in turn reduces the pressure on the water at the bottom. And from there, this decreasing pressure on the bottom causes boiling, and some of the bottom water flashes to steam, and that ultimately results in the geyser eruption. And this is cyclical too. If you've ever been to Yellowstone Park, Old Faithful, they actually timed the next geyser eruption. What happens is that after the geyser erupts, the emptied chambers will then fill with more groundwater. That groundwater gets heated at the bottom, and the cycle continues. And we get these spectacular geyser eruptions as a result. Yeah. Iceland geysers may have a little bit different type of plumbing system, but still, Iceland has a lot of hot springs and geysers because, remember, Iceland is part of the Mid-Atlantic Ridge, exposed above sea level, and there's a mantle plume that's pushing it up. So it's no wonder that Iceland is volcanically active and a source of basically a lot of geothermal activity.
So is Iceland mainly of basalt?
Yeah, in the case of Iceland, it's mainly basalt, but they could have other types of igneous rock. But the source of the heat is the underlying magma activity. But this map here shows the location of the hot springs and geysers throughout the United States. Closer to homes, we have Hot Springs, Arkansas. I don't know for sure, but I think those hot springs are a result of deep penetration of groundwater. There are a lot of deep buried faults within, particularly the Ouachita mountain system in Arkansas, and that might be what's heating up that water. I'm not quite sure, but I suspect that's the source. But notice that most hot springs and geysers tend to be associated with ancient mountain systems. And again, it's because of the deep faults that groundwater can penetrate deep below the subsurface. And also out west, there could also be deeper magma systems too, particularly under the basin and range of Nevada, where magma can occur at great depths. But anyway, here's our favorite slide, end of lecture. What did I